Okay, so in this short course, we've touched on a whole bunch of interweaving, interrelated topics. We started out separating mixtures, figuring out the difference between compounds and mixtures and elements, and then we dove in and actually measured some properties of various substances just to see how scientists, how chemists characterize various things. Then in chapter 2, we dug into the even kind of more, I would say, philosophical or deep questions in this period in chemistry. Again, we're in the early 1800s, late 1700s. Chemistry is a new science. And the first big question, or one of the first big questions we looked at is, are there similarities or groupings amongst this newly increasing amount of pure elements that were being discovered in this period? It was a wonderful period in chemistry. And our answer at this point in time is yes. Scientists were seeing, like, okay, there's a set of metals we'll call alkali that all share similar properties. They're all very reactive, they're very soft, they're very shiny. There's another set of similar metals called the alkaline earth metals that would share a set of similar properties. And then on sort of the other side, the non-metal side of things, there's a set of gases. Actually, they're not all gases, because iodine is included in this. There's the halogens. They all have a similar set of properties, mostly related to their reactivity, meaning they all kind of bond. Pick another element like titanium or sodium. All the halogens react with these elements in similar ways. So the answer is yes, there are groupings emerging out of these increasing number of elements being discovered. A second question is, why do compounds made of multiple elements have such different properties from the elements that make them up? So why do compounds have such different properties than the elements that made them up? We touched on this theme many times, and at the beginning it was a mystery. So you can imagine in the 1700s, this was quite mysterious, and there was no way to answer this question. Now, with just a few labs, we have a definitive, or at least a strong hunch of what's going on here. And the reason why they're so different, it's actually, it actually has to be that way. So, and we can answer it in terms of like chemical reactivity. So again, the more reactive an element is, by definition, the compound is less reactive. So it's almost like a defining thing that elements have to be different than the compounds that make them up. And a third question, we read here in the launch write-up, is why do similar elements like sodium and potassium or chlorine and bromine react similarly? And so we have an idea, and I just mentioned this with the halogens, so we know that's what groupings are based on, is how they react. And so our hunch, certainly addressed in chapter 4, is that it may have to do with how elements interact with electrons. Because after all, if groupings are based on reactivity, and our sense is, our hypothesis, our working hypothesis is that reactivity is a function of, is an electrical phenomena. It's a function of, perhaps giving up or interacting with electrons in some way. If similar elements interact with, have a similar relationship with electrons, that's the defining feature of that group. So those are three big questions: similarities among elements, groupings among elements, the difference between elements and their compounds, and why similar elements seem to react similarly. So in this final chapter, let's dig in to this third question: how do we explain the relationship between metals and electrons during a chemical reaction or in chemical reactivity? And to do this, we're going to have to take a look at this amazing invention we used in short course 1, the chemistry of atoms, the battery. Alessandro Volta's invention, originally called the voltaic POW, now we call it the battery. We're going to dig into how this thing works to make sense of this answer. But to do this, let me get my trusty whiteboard. So his invention was strikingly similar. In fact, you may remember, I think I touched on this before, making a simple battery with two metal electrodes or metal pieces, just sort of spearing them into a lemon, bam, out comes electricity. So just another way to think of this is a lemon is just, a liquidy substance that has stuff in it. We call it electrolytes. So if I have water here, and let's say this is dissolved with sodium chloride or baking soda or sodium sulfate or sort of anything that can dissolve, Na plus, Cl minus, Na plus, Cl minus, so this is sodium chloride, Na plus, Cl minus. So it's sodium chloride dissolved in this, and I stick two metals in it. Pick your element. So I'll call that copper, and we'll call this, maybe magnesium. And I hook a wire between it, and maybe I have like a little light bulb there, and bam, electricity will form just as is. There's nothing else I gotta do. It's that simple. A battery is nothing but two different metals in what we call an electrolyte. So our key thing here in terms of building up an explanation relating metals and electrons during chemical reactions is to play around with different types of metals in this battery, because evidently you may be able to just deduce right off the bat is that batteries work because of what's going on right at this interface, at the metal solution interface. And you can actually deduce this by simply pulling one of these metals out of your lemon or your electrolyte solution, and then you'll see the light bulb go off. So however this is working, we know both metals must be touching the liquid, and if both metals must be touching the liquid, the simple deduction is that there's something going on between the liquid and the metal. And we don't know what's going on. That's what we're going to try to experiment with. And to do that, let's just take metals: magnesium, aluminum, iron, copper. And so magnesium here, I'll call this aluminum. Where's my green? So if I have aluminum and magnesium, all you have to do is make your electrolyte solution with a little beaker, a little table salt or sodium chloride. You can make your electrolyte solution. Then you, bam, aluminum, magnesium, stick them in the water, hook them to a wire, and then instead of a light bulb, we're going to use a little LED. There's little quirks around using LEDs as opposed to light bulbs, but the nice thing about LEDs is they take a very low amount of current, amount of electricity to get them working, so it kind of ensures this experiment works. And yes, LEDs did not exist in the early 1800s, but we'll take what I call a poetic license here and use it for the sake of our work.